appreciate you for organizing this. It's extremely valuable for me, particularly for this subject I'm going to discuss, because you'll see I'm still working through this. It's not because I didn't think about it very much. I started on trying to do this project before the Akari launch. So that means when many of you were babies. And so, of course, other people had the idea also, but I'm not sure exactly the best way to do this. How can we use this incredible set of unique data from Akari NEP field to construct useful, realistic family of optical infrared energy distributions that describes a lot of galaxies in the universe? Right, so I really do believe that this is a very important legacy for Akari deep fields. And of course, it depends on a number of things, which we all have. So we need multi-wavelength data. We have the multi-wavelength data. We need the 9-filter coverage, and we need a wide area to find many kinds of bright infrared galaxies. And in my opinion, we also need to have accurate redshifts. So that means it was necessary to do a lot of spectroscopy after Akari measured the objects, so that we know what the rest frame wavelengths of each of these observations in each band of IRC is. So now we have actually a pretty large sample, as you will see, because there was a lot of spectroscopic follow-up with various telescopes here. A lot of hard work was done. There is, of course, a bias here. In addition to the bias that the objects that are in the sample should be bright in the Akari bands, including the mid-infrared. It also helps if they have some emission lines in the optical spectrum so that we can identify it. This is not absolutely crucial requirement, but this one is a serious requirement. I really want to have detections, not upper limits, but detections for all of the Akari IRC filters. So if you have a galaxy which is not very active, does not have very much warm dust emission, then there are fewer of them in the sample. So we cannot draw a general conclusion about all kinds of galaxies, but we can draw good conclusions about infrared emitting galaxies. Now, so here I'm going to tell you the guts of the procedure, step you through it, and this is messy. So it's at the beginning of the morning, so you're ready to get your hands very dirty. I mean, this is not machine learning at all. This is stupid human learning, and maybe the opposite. So maybe you won't believe how primitive this is, but all I say is, well, it's based on the data, and it is very simple, because I'm very worried about trusting a very complicated mathematical process, although I really want to try this also with our experts on this. So all I did was to get hundreds of rest frame spectral energy distributions from rest frame ultraviolet, basically, to rest frame infrared, and just plot them, make a paper plot on the same scale, log of flux versus log of wavelength, and normalize them to maybe the V band. That's what I did. And then I just slide on top of each other these different papers. I have hundreds of these papers, and trying to match them. Do I see some SEDs which look very similar to me from different galaxies? Maybe, this is an important point, at different redshifts, but it looks the same to me. So we can interpolate with different redshifts. We can interpolate between these rather wide Akari filters, wide band passes. So after looking at this a lot, we came up with, this is really ad hoc. You know what ad hoc means. We're just making this up. So it's not based on scientifically precise principles that I could tell you what it is. But we could come up with about 14 different groups of galaxies which to us look quite similar among the galaxies in one group, and they look different from the SEDs of other galaxies. And then the point, of course, is to get a lot of galaxies into a group so you can make a good average. Okay, each individual galaxy won't be exactly perfect, but if you have dozens of galaxies in a group, I hope the idea is I could make a good average galaxy SED. So to quantify this, I tried to quantify this, the correlation coefficient of two galaxy spectra, if it's greater than 0.95, I would say that those galaxies for us are in the same group. It's just the same kind of spectrum, maybe not exactly the same, close enough for us. But if the correlation coefficient is less than 0.9, then I say that's a different group, not the same. And this is just strictly empirical. I'm not giving any astrophysics. I didn't say why the spectra are different yet. Now, the interesting point about, one problem about this procedure is that I think maybe 40% of all of the galaxies that we looked at did not meet the condition of a high correlation coefficient with any of the groups that we made. So we could not classify them. I mean, I can tell you which template spectrum they're closer to, but I don't know which is the right one. Anyway, so a lot of this might sound to you like we're doing principal component analysis of the spectra, but anyway, I just want to do it empirically. So the problem with some of these other methods, as we've discussed, is that I might not understand how to interpret the answers. All right, so we have a total now, because of so many redshifts and so much data, about 1,700 spectral energy distributions where we know the rest wavelengths. And so it's a mixture, somewhat more from NEP wide. I'm not sure, is there always 24 micron data or not for NEP wide?
There is.
Okay.
It's regardless of detection. I mean, it's shallower.
It's shallower. Okay, so maybe in many cases we couldn't detect it. But anyway, even if we can detect to 18, and 24 is better, then at least we can make the spectral template for a typical redshift of a half. We can make a spectral template out to a rest wavelength of 13, 14, 15, 16 microns, which is an interesting region. So of those 1,700, we worked with 900 of them, which is enough. It's enough of them to classify, 900 of the 1,700 belong in one of these 14 groups. So it means we have an average of 50 or 60 galaxies in each group. Some have 80 galaxies, some don't have as many. And so because they're at different redshifts, I think we can, I'll show you, we can get an idea of what the average spectrum is. All right, so the typical redshift, as I said, is 0.5. Plus or minus from 0.3 to 0.7 of the different galaxies. The high luminosity galaxies here would be at a bit of a higher average redshift. And then there are some galaxies we're interesting to have which have very weak infrared in them. They're like early type galaxies, and those are less luminous. They're at low redshifts. But that's okay. Anyway, so I'm just going to spend a few minutes, if we have time, to look at some of the actual group examples. Here are 5 examples. So here are many individual galaxy SEDs. I'm just connecting the different filters there, even though these filters are very wide. And then they've been normalized in the visual band. And so this is probably the most average SED you can find in NEP deep field, or NEP. And so then you can have some judgment what kind of smooth curve, I'm just using cubic splines, can you put through the data that approximates the galaxies, all these different galaxies. And so if you want to preserve too much information, you can allow high frequency wiggles in there from the spline. Maybe that wasn't a good thing to do, or you can force it to be smoother. I wanted to preserve the possibility for some spectral features from PAHs. And please, in all of the graphs, just forget about what happens at the end. That's just, the data runs out and the spline does some crazy wiggles. But just stop about there. And okay, so that's one example of it, based on 67 galaxies. So, by the way, these 14 different templates, it's complicated. You cannot describe them simply with a few different colors. For example, this is basically how red the galaxy is. X-axis is 10 microns divided by 1 micron. So that's the warm dust compared to the starlight continuum. The vertical axis is attempting to measure strength of PAH, comparing 7 wavelength to 4 micron. These are rest frame wavelengths. But you can see that the different groups, which have different colors, we've had a lot of fun with the colors here, have many different properties here, which cannot really, some of the groups appears in this diagram to be on top of each other, but they are different, actually. So there's a lot more information than you think in these different templates. So for example, I showed you the most typical galaxies, which are these pink ones. Now let's look at the red circles here. The red circles have about the very strong infrared continuum, and they also have very strong PAH bump. And here's what they look like. So, I mean, you can just see the PAH bump at 7.7 is in there, and it's very strong, and that's all right. So, let's see. Another example here, on the other side of the diagram, look at these blue circles here. They also appear to have a very strong PAH, but on the other hand, they have relatively weak infrared emission. So that looks like, that group looks like this. Very strong PAH bump there, but not such a strong infrared continuum. Continuum is fairly weak. Remember, this is Jansky F sub nu units, so there's not much energy in the infrared in those galaxies, except in the PAHs. Let's see, then moving down to even weaker dust, the galaxies look less active. We have the blue asterisks here, which are fairly weak PAH, fairly weak dust. Just to give you some examples of the different variety, and so you can see it just, the starlight bump is strong, and then it's sort of flat over there. Don't really see much indication. It's not just a question of PAHs, or just a question of hot dust, or just a question of cold dust. All of these different parameters gives you some different kind of template. And finally, this is almost in a class by itself. These objects here with the pink asterisks has almost no cross-correlation coefficient with any of the other samples. They're really in a category just by themselves. And you see they have very, very weak infrared dust emission. So I think of these as early type galaxies, perhaps. And we don't have too many of them. So how to connect all of these 14 different templates? I showed you some examples. Well, of course, there's a very informative diagram. You can make the cross correlations of each of the templates, which we gave these silly names to, and you can see, for example, that some categories are very similar. We both label these green because they have similar coefficients. They're very similar to each other, but we decided in the end that we could separate them from other categories. Dramatically different categories are these, basically AGN category here, that has a straight, very strong hot continuum due to dust that's warmed by the AGN. This one here I showed you, this is the early type galaxies. It's anti-correlated with the other samples. So anyway, you take all the I took all the information from this matrix here, and I decided to play a game in my office. So this looks like a game of dominoes here. Can you see this? Each of these cards is the name of one of these 14 groups. And so I started putting them on my desk. In the closest ones, which have the highest correlation, are physically close to each other. These two green groups, almost identical, very similar, but slightly different. Two yellow groups are very similar. And so I put them around. But this group, this one is not really, it's similar to this one, but not similar to any of the others. This one is I showed you, is most similar to this one. Anyway, and you can see, although there is a general trend from very weak infrared continuum to a strong dust continuum, there are other factors going on here which we don't really have an explanation for. This category here I have to hold in my hand because it's above the diagram. It's somewhere up here. There's other differences that are not summarized here. So there are several parameters that must be going on. Anyway, if you want to look at all of them together, you'll get an idea of how it's rather complicated. Again, don't worry about the wiggle at the very end of it, but those are the 14 templates. Okay, so you can see the AGN template is pretty much what you expect that one to be. And then this is the early type galaxy one. And you see some trend to have more dust, but there are many other differences. How deep is the minimum between the starlight and the dust at 4 to 5 microns? How strong is the PAH emission? In some cases it's not visible, in some cases it seems to be dominating. So I would think any simple model, which I suppose we could make, would have to have at least 4 components which can change independently of each other if you wanted to match all of those different specs. I mean, you notice that they cross each other. So since they cross, that means that there must be, it's not simply a one-parameter family at all. These don't really agree that well with the famous Roberta Asef templates that have been published. This is what everybody uses now. I think we are going to do better by having Akari templates. And my final conclusion here, just to put this in front of you, is we don't have it's strictly empirical. We don't have a physical interpretation. What is astronomically different about these galaxies? because it's a classic problem where you want to know what the spectrum is, but you only have these broad filters which are not perfect rectangles that are convolved with the spectrum. You have to deconvolve. And so what we really need, and this is amazingly difficult to do, is to get as many filters from Akari IRC as we can, photometry, of the same galaxies which has an infrared spectrum. Maybe from Akari, GRISM, or maybe an infrared spectrum from Spitzer IRS. And then we can compare them directly to say, well, this template looks very much like this galaxy. So maybe the spectrum is the same, for example. Anyway, so of course this is an example of trying to do this. But really, nobody ever calibrated the Akari filters, SED, with actual infrared spectra, really. I think to show that how they can be compared directly. Anyway, so that's what I wanted to do, and I really appreciate to have questions, and I know there are going to be criticisms and suggestions from you guys, because you see this is still work happening. Okay, thanks.
Thank you. Questions?
Yeah.
So probably the number of groups could be determined by the number of the first person you choose to.
That's right. So if we accepted rather poor correlations like 0.85, then there would be smaller number of groups. It's a judgment.
The following question would be: so you want to correlate or find the correlation between your groups and other physical parameters like morphology or other physical parameters.
That's a great idea. Yeah.
I don't know whether we have any.
Yeah, it's a good idea, like maybe emission line properties and so on. It's a great idea. So I haven't done it yet. My general impression is that the groups, well, first of all, the AGN groups are probably going to show indication of a highly ionized active nucleus. But the other groups, we have some groups which have stronger dust emission, at least the stronger dust emission of strong infrared continuum, I expect will be associated with high star formation rates, maybe strong emission lines from H alpha and so on. But it's not yet done, so it's a very good suggestion.
Very simple question. How many bands do you use for the SEDs, and is it the same for each SED? I mean, do you have SEDs with holes in the spectra or not?
So that's a bias. I really don't use anything that has holes in it, pretty much, because I'm just too worried about it. So these are pretty complete. The Galax filters are down here, that's not as complete, but now in the NEP wide, at the moment we were limited to only Maidenac data, which is B, R, and I. I didn't really care very much about what was happening in the optical, to be honest with you. Yeah, so I was worried about that. So if there is one filter missing, we don't really want it. Except sometimes we could not get 24 micron filter. That's a good question. Yeah. Otherwise we could have more galaxies. I mean, of course, new galaxies will be observed by JWST or other people, and then they will have, I don't know what filters on them, and then of course they could be correlated with these templates, and I suppose one of them, I hope, will describe it. With some new filters. Yeah, well,
I think I have two comments. I think it's very important to compare the Anetska's 7 years machine learning.
yeah.
And also, it's interesting to fit like Dennis's cigar to.
Yes, that's one thing we're trying to do. Yeah, in fact, I was talking to you last night about it. But clearly, he needs. I have to use the most powerful version of your program, which has a sophisticated treatment of dust, which allows me to change independently of other things strength of pH.
Yeah.
Otherwise, I cannot really understand the difference between these. But since you now include that in the model, that's our next thing to do. I think it should be interesting. I mean, right, that's an attempt to interpret what is the underlying astrophysics between all of this empirical mess, basically.
Well, if you have data, if you give it to Tina, then she can do it by tomorrow.
Oh, okay, maybe we should. All right, Tina, that's
Or
nice.
maybe after her talk.
Okay.
Yes, that would be better. Yeah, we'll talk later.
I have one question. When you do you go to the...
Oh, I forgot to say, can you see how that's the 7.7 wavelength, and you can see sometimes there's a big bump there, but other times there's really nothing going on there. And I can't decide if there's a little bump at 11 microns, that's a weaker PAH feature.
Okay, related to that, do you use the uncertainties on the flux when you do the correlation? When
Do
you
I use the which?
So it's the uncertainties, the errors. Because here, probably you have larger
It's worse.
errors. And
Yeah.
some of the difference might disappear if you assume that you have larger uncertainties, especially in this part where you know it's moving a lot.
I'll look at that. I'll look at that. I mean, the formal uncertainties are fairly small.
Oh,
I mean, remember, this is a factor of 10 difference here, and so if you have something...
yeah, but between, I don't know, this one and this one,
Yeah, it's a good question. Yeah, I mean, it is arbitrary that we divide it, as you said, into this many groups. Yeah, and for any one galaxy, which has noisy data, we could certainly question it. Okay, I'll look at that.
Any other question? Yes.
Could you be more specific about difference between hot dust and warm dust?
Okay, so the hot dust is producing the emission on the short wavelength side of PAHs. How deep this valley is, or how fast it comes up. So I guess it's dust which is capable of emitting at 5 microns or 6.
One temperature has very deep.
Some of these, yeah, this is probably an artifact of the spline, but some of them are very, very deep, and others seems to be filled in. And that's different from the warm dust that emits at 10 microns. I mean, they don't always behave together.
So you discriminate PAH and warm dust.
We're trying to, yeah, I mean, yes, otherwise, yes, if this can do anything, because we have, we have filters here, so, yeah, that's, I hope so, yeah, definitely.